Look up at the night sky. What do you see? A scattering of stars, maybe a planet or two, the distant glow of the Milky Way. But what if I told you that beyond those familiar pinpricks of light lies a universe teeming with mysteries so baffling, even the brightest minds on Earth can't explain them? We've sent probes to the edge of our solar system, built telescopes that peer billions of years into the past, and yet space still holds secrets that defy logic, physics, and sometimes even common sense. From eerie radio signals to planets that shouldn't exist, the cosmos is a puzzle box waiting to be opened, and today we're diving deep into 30 of its most jaw-dropping enigmas. Imagine a galaxy where stars vanish without a trace, where black holes hum melodies we can't decipher, or where entire planets rain molten glass sideways. These aren't plot twists from a sci-fi novel, they're real phenomena happening right now, light years away, and they're rewriting everything we thought we knew about the universe. Scientists scratch their heads, theories collide, and textbooks gather dust as these mysteries stubbornly refuse to be solved. But that's the thrill of exploration, isn't it? The moment we think we've got space figured out, it throws us a curveball, something so strange, so utterly unexpected, that it leaves us equal parts awestruck and unsettled. So why do these cosmic riddles matter? Because they're not just curiosities for astronomers, they're invitations. Invitations to wonder, to question, to marvel at how little we truly understand. Whether it's a signal from the void that repeats like clockwork or a planet so dark it absorbs nearly all light, each mystery is a doorway to something grander, a reminder that the universe is far weirder and far more wonderful than we could ever imagine. Buckle up, because we're about to embark on a journey through the unexplained, where every twist will leave you asking, what else is out there and how much stranger can it possibly get? Now let's start where the confusion runs deepest, with a signal from the cosmos so bizarre, it's been called the wow signal for over 4 decades. In 1977, a radio telescope in Ohio picked up a burst of energy so powerful, so unmistakably artificial seeming, that the astronomer who discovered it scrawled, "Wow," in red ink right on the data printout, and then nothing. The signal never repeated. Was it an alien hello, a cosmic glitch? To this day, no one knows. But it's just the first of 30 mysteries that'll make you question everything you thought you knew about the universe. That red-inked wow scrawled across the data sheet wasn't just excitement, it was pure bewilderment. For 72 seconds on August 15, 1977, Ohio's Big Ear radio telescope locked onto a signal so intense it dwarfed all cosmic background noise. The frequency, exactly 1420 MHz, the forbidden zone where earthly broadcasts are banned to avoid interfering with deep space listening. The signal's shape, a perfect spike, rising and falling like a cosmic heartbeat, matching how a distant transmitter would appear as Earth's rotation swept the telescope's gaze across the sky. And then, as abruptly as it started, silence. Scientists rushed to test every logical explanation. A passing satellite, none were overhead, military activity. No records matched, a natural phenomenon like a quasar. The signal was too narrow, too clean, like tuning a radio to one station and hearing crystal clear music instead of static. Even stranger, the signal originated from a patch of sky near the constellation Sagittarius with no known stars or planets. For 47 years, astronomers have pointed every available dish toward that spot, hoping for a repeat. They've heard nothing but the usual cosmic whispers. The theories range from plausible to downright spine-tingling. Some suggest a comet's hydrogen cloud could have emitted the frequency, except comets don't vanish without a trace. Others propose an interstellar lighthouse, a beacon from a civilization deliberately signaling the cosmos. Then there's the unsettling possibility we caught a one-time event, a dying alien transmission, perhaps, or a technology so advanced it defies our detection methods. Even SETI senior astronomer Seth Shostak admits the WOW signal checks every box for what an intelligent signal should look like, except the most crucial one: it won't talk back. What makes this mystery endure isn't just the unanswered question. It's the tantalizing proof that something out there, whether natural or not, can still make our best instruments scream in surprise. The WOW signal reminds us the universe isn't just vast, it's playful, hiding its most thrilling secrets in plain sight, if only we know how to listen. And just when we think we've ruled out every possibility, space whispers try again. If the WOW signal left us scratching our heads, dark matter makes us question the very fabric of reality. Picture this: every galaxy spins so fast that stars at its edges should be flung into the void, yet they aren't. Something invisible, something massive, holds them in place with gravitational handcuffs we can't see. That's dark matter, an enigma making up 27% of the universe, outweighing all visible matter 5 to 1. We know it's there because galaxies move like puppets on unseen strings, light bends around empty space, and the cosmos behaves as if haunted by ghostly mass. But catch it in a lab, not a chance. For 80 years, scientists have chased this phantom. They've built detectors deep underground, shielded from cosmic noise, waiting for a single bump, a whisper of dark matter brushing against ordinary atoms. So far, silence, the leading suspects, WIMP, weakly interacting massive particles, theoretical heavyweights that barely acknowledge normal matter except through gravity. Then there are actions, hypothetical ultralight particles flitting through space like cosmic fireflies. Some experiments claim faint hints, but others contradict them. It's like hearing footsteps in a dark room, only to flick on the light and find nothing. The frustration is poetic. We're swimming in an ocean of dark matter, yet it slips through our fingers like smoke. Every failed detection tightens the mystery. Maybe dark matter isn't particles at all, maybe gravity itself works differently on cosmic scales. Or perhaps we're like fish, unaware of the water they swim in, missing a fundamental layer of reality. One thing's certain: until we solve this riddle, we're only seeing half the universe. The rest, a shadowy ballet of the unknown, dancing just beyond our grasp. And speaking of shadows, our next mystery doesn't just hide, it devours. Not even light escapes its pull. Dark energy is the universe's best-kept secret, a force so strange it makes dark matter seem almost ordinary. Picture a balloon inflating faster and faster, not because you're blowing harder, but because the rubber itself is stretching on its own. That's what's happening to our cosmos. In the late 1990s, astronomers studying distant supernova made a jaw-dropping discovery. The universe isn't just expanding, it's accelerating. And the culprit, something invisible, something relentless, pushing galaxies apart at speeds that defy gravity's pull. They called it dark energy, and it's rewriting physics as we know it. Einstein might have been the first to brush against this mystery. His equations once included a cosmological constant, a fudge factor, to keep the universe static. He later called it his greatest blunder when Edwin Hubble proved the cosmos was expanding. But now, dark energy has resurrected the idea in a way even Einstein couldn't foresee. This isn't just some minor tweak to gravity, it's a fundamental upheaval. Dark energy makes up 68% of the universe's total energy, yet we have no clue what it actually is. Is it the fabric of space itself stretching, a new kind of energy field, or proof we're missing an entire chapter in the laws of physics? The cosmic microwave background, the afterglow of the Big Bang, holds vital clues. This faint radiation, captured by satellites like Planck, shows tiny temperature variations that map how matter clumped together in the early universe. But here's the twist: those patterns reveal space is geometrically flat, meaning its total energy density matches a critical value. Ordinary matter and dark matter only account for a third of that. The rest, dark energy's fingerprint. It's as if the universe left us a receipt, and 68% of the total is blank. The implications are staggering. If dark energy keeps accelerating expansion, distant galaxies will eventually vanish beyond an unreachable horizon, leaving future civilizations with a night sky almost empty. Some theories suggest dark energy's strength might change over time. Could it one day rip atoms apart in a big rip? Others propose it's not a force at all, but a sign our understanding of gravity is fundamentally flawed. The truth is, every telescope, every supercomputer simulation, every lab experiment has hit the same wall. Dark energy doesn't interact with anything we can detect. It's the universe's silent puppeteer, yanking the strings while remaining utterly invisible. What makes this mystery so electrifying isn't just the unanswered questions, it's the sheer audacity of a universe that refuses to sit still. Dark energy whispers that everything we think we know might just be the tip of an incomprehensible iceberg. And until we solve it, we're left staring into the void, watching the cosmos run away from us faster than we can chase it. If the universe is so unimaginably vast with billions of galaxies, each containing billions of stars and planets, then where is everybody? That's the unsettling question at the heart of the Fermi Paradox. Named after physicist Enrico Fermi, who famously blurted it out over lunch in 1950, this cosmic riddle cuts to the core of our search for meaning in the cosmos. The numbers say extraterrestrial civilizations should be everywhere, even if only a tiny fraction of planets develop life and a fraction of those produce intelligent species. The Milky Way alone should be buzzing with activity. And yet silence, no interstellar radio chatter, no alien megastructures, not a single definitive sign we're not alone. The contradiction is so glaring, it's either a flaw in our logic or a chilling hint about the nature of life itself. One terrifying possibility, the Great Filter. Imagine an invisible wall, a near impossible hurdle that stops most life from advancing beyond a certain point. It could lie in our past. Maybe complex life is rarer than we think, or self-destructive tendencies like nuclear war are universal. But the darker scenario. The filter is ahead of us. Perhaps every civilization hits a technological wall, climate collapse, rogue AI, or some unseen catastrophe and vanishes before they can colonize the stars. If true, our search for aliens isn't just curiosity, it's a race to see if we're next. Then there's the zoo hypothesis, the idea that advanced civilizations know we're here but deliberately avoid contact, treating Earth like a cosmic nature preserve. Maybe they're observing us until we reach a maturity threshold, or hiding like parents letting a child learn on their own. It sounds like sci-fi, but it would explain why SETI telescopes hear nothing. Or consider the sheer scale of space. The nearest star is 4 light-years away. A radio signal from there would take 8 years for a two-way chat, hardly practical for conversation. By the time a civilization could bridge those gaps, they might lose interest in primitive species like us, just as we don't seek out ants for dialogue. The Fermi Paradox isn't just about aliens, it's a mirror. Every theory reflects our hopes, fears, and biases. Are we special, doomed, alone? Until we find proof, the silence of the cosmos remains the loudest mystery of all, a void filled not with answers, but with possibilities as infinite as space itself. Most stars flicker gently, their light dimming and brightening in predictable rhythms, but not Tabby's star. Nestled in the constellation Cygnus, this unassuming yellow dwarf behaves like nothing else in the cosmos. In 2015, citizen scientists poring over Kepler Space Telescope data spotted something bizarre. The star's light didn't just dip slightly, it plummeted by a staggering 22% at times, as if something colossal was passing in front of it. And these weren't regular planet-like transits. The dimming was erratic, asymmetrical, and utterly unpredictable, like a cosmic strobe light with no off switch. Early explanations pointed to a swarm of comets, thousands of them, trailing enough dust to blot out a fifth of the star's glow. But comets don't explain the historical data. When astronomers dug through century-old photographic plates, they found something even weirder. Tabby's star had faded by nearly 14% between 1890 and 1989. Stars this size shouldn't dim so dramatically over such a short cosmic timescale. Comets might obscure light temporarily, but they can't account for a century-long dimming trend. That's when the theories got creative. Enter the alien megastructure hypothesis. Some researchers floated the idea of a Dyson swarm, a vast array of energy-harvesting satellites built by an advanced civilization, partially enclosing the star. The irregular dips may be massive construction projects with panels shifting in and out of view. It's a tantalizing thought, but scientists quickly pumped the brakes. Extraordinary claims require extraordinary evidence, and Tabby's star wasn't making it easy. Observations revealed another twist: the dimming wasn't uniform. Some wavelengths of light were blocked more than others, suggesting fine dust, not solid megastructures, was the culprit. Yet even that doesn't solve the puzzle. Dust should be blown away by stellar radiation unless something's constantly replenishing it. Could it be planetary collisions, a disintegrating moon? Or something we haven't even dreamed up yet? Today, Tabby's star remains under relentless scrutiny. Telescopes like the James Webb Space Telescope are analyzing its light for chemical fingerprints, while amateur astronomers worldwide track its every flicker. Each new observation raises more questions. Why does it dim more in some colors than others? What's causing those strange, sharp dips that last for days? What makes this mystery so captivating isn't just the lack of answers, it's the sheer audacity of the possibilities. Tabby's star challenges us to think bigger, to question whether we're seeing natural chaos or the fingerprints of intelligence. Until we know for sure, it stands as a cosmic Rorschach test, a reminder that sometimes the universe's most baffling behaviors are the ones that push science forward. One moment the cosmos is quiet, the next boom, a blast of radio waves brighter than entire galaxies erupts across the universe, then vanishes in less time than it takes to blink. These are fast radio bursts, or FRB, some of space's most explosive head-scratchers. Imagine tuning your car radio between stations and suddenly catching a deafening, 1-second scream from billions of light years away. That's essentially what telescopes detect, except these bursts pack more energy than the sun emits in months. And the wildest part, we still don't know what's screaming. The first FRB was spotted in 2007, buried in archived data from an Australian radio telescope. At first, astronomers debated whether it was even real, maybe a glitch or a microwave oven left running in the observatory kitchen. But then more detections poured in, each one a millisecond-long mystery pinpointed to distant galaxies. Some burst once and never repeat, like cosmic firecrackers. Others, like FRB 1211-2, pulse on unpredictable schedules, flickering dozens of times from the same patch of sky. It's as if the universe has both sporadic shouters and chronic chatterboxes, and no one knows why. Then came the Magnetar connection. In 2020, a highly magnetic neutron star in our own galaxy, a magnetar named SGR 1935 plus 215, let out an FRB-like scream. Finally, a smoking gun, these ultra-dense stellar corpses, spinning with magnetic fields a trillion times stronger than Earth, could twist themselves into energetic knots until snap, they release bursts. But here's the catch: magnetar flares don't match the raw power of the biggest extragalactic FRBs. It's like comparing a firework to a supernova. Plus, repeating FRBs often come from serene regions of space with no magnetars in sight. So while magnetars might explain some bursts, they're not the full story. The plot thickened in 2022 when the Canadian CHIME telescope detected an FRB originating inside a globular cluster, a dense ball of ancient stars where magnetars shouldn't exist. Theory says these stars are too old to produce such young, volatile objects. Then there's the Walmart parking lot, FRB, which came from a galaxy so ordinary, so utterly unremarkable, it defied expectations that these bursts need extreme environments. So what else could they be? Theories range from colliding neutron stars to evaporating black holes, or even, yes, alien propulsion systems beaming energy across galaxies. The truth is, FRBs might not have a single origin. They could be cosmic breadcrumbs leading us to multiple undiscovered phenomena. Every new detection adds another piece to the puzzle, but the full picture remains frustratingly out of focus. What makes FRBs so thrilling isn't just their mystery, it's their potential. Like cosmic lighthouses, their signals get distorted as they travel through intergalactic gas, letting astronomers map the invisible matter between galaxies. And if we ever decode their origins, we might unlock new physics or even, well, let's not get ahead of ourselves. For now, these fleeting radio screams remind us that the universe loves a good plot twist, especially one that lasts just a thousandth of a second. Our Milky Way isn't drifting through space aimlessly. It's being pulled towards something massive, something we can't even see directly. This invisible force, known as the Great Attractor, lurks about 250 million light-years away in the direction of the constellation Centaurus. But here's the catch: it sits squarely behind the zone of avoidance, a region of space obscured by thick dust and stars from our own galaxy's disk. It's like trying to spot a lighthouse through a hurricane, except this lighthouse is tugging entire galaxies toward it at over 14 million miles per hour. For decades, the Great Attractor was more of a gravitational rumor than a confirmed phenomenon. Astronomers first noticed something odd in the 1970s when mapping the cosmic microwave background, the afterglow of the Big Bang. The data revealed our local supercluster of galaxies wasn't just expanding with the universe, it was also sliding toward some unseen mass. The problem: the Milky Way's dusty plain blocked optical telescopes from seeing what lay beyond. It wasn't until infrared and radio telescopes like NASA's and South Africa's MERKT pierced through the cosmic fog that the picture began to clear. What they found was both awe-inspiring and humbling. The Great Attractor isn't a single object but a sprawling confluence of galaxy clusters, with the Norma cluster at its heart, surrounded by hundreds of thousands of galaxies bound together by gravity. This supercluster, dubbed Laniakea Hawaiian for immeasurable heaven, spans 500 million light-years and contains roughly 100,000 times the mass of the Milky Way. Yet even this colossal structure might not be the end of the story. Some scientists suspect the Great Attractor itself is being pulled toward an even larger anomaly, the Shapley supercluster, a gravitational titan 8 times more massive, located over 600 million light-years away. The implications are staggering. Our cosmic neighborhood isn't just expanding, it's flowing, a vast river of galaxies channeled by gravitational currents we're only beginning to map. Infrared observations reveal filaments of dark matter weaving these clusters together like invisible threads, while galaxies move along these highways like cars on an interstate. The Great Attractor is just one hub in this cosmic web, a reminder that even on the grandest scales, gravity's pull shapes everything, but the mystery isn't fully solved. Why is the Great Attractor's pull stronger than its visible mass suggests? Is there more dark matter lurking there than we've accounted for, or are we misreading the motion of galaxies? Every new infrared survey peels back another layer of dust, offering glimpses of previously hidden galaxies. Some with supermassive black holes firing jets of energy toward us, others colliding in slow-motion dances that reshape entire regions of space. What makes this enigma so compelling isn't just the scale of the forces at play, it's the sheer audacity of our quest to understand them. We're like ants tracing the contours of a mountain we can't see, guided only by the tug of its gravity. And as telescopes grow more powerful, the zone of avoidance is slowly lifting its veil, revealing a universe far more dynamic and interconnected than we ever imagined. Up next, another hidden heavyweight, but this one doesn't pull, it pushes. Dark energy's cosmic repulsion is rewriting the fate of the universe. Oumuamua wasn't just another space rock. It was our first confirmed visitor from another star system, and it broke every rule in the book. When the Pan-STARRS telescope in Hawaii spotted this strange object zipping through our solar system in October 2017, astronomers expected a typical comet or asteroid. What they got was something straight out of science fiction. A sleek, reddish object up to 400 meters long but only 40 meters thick, shaped like a cosmic pancake tumbling end over end. Its trajectory screamed interstellar, but its behavior was anything but ordinary. The first jaw-dropper, Oumuamua accelerated as it left the sun's vicinity, something icy comets do when their frozen gases heat up and jet outward. But here's the catch: no coma, no tail, no visible outgassing. Telescopes scoured every wavelength and found zero evidence of water or carbon dioxide vaporizing off its surface. This thing was as dry as a bone, yet it moved like it had invisible thrusters. Scientists scrambled for explanations, maybe hydrogen ice sublimating in a way we couldn't detect. Perhaps radiation pressure shoving its weirdly thin shape. Each theory felt like squeezing a square peg into a round hole. Enter Harvard astrophysicist Avi Loeb with a provocative idea: what if Oumuamua wasn't natural at all? His controversial hypothesis suggested it might be artificial, a light sail from an alien civilization, thin and reflective by design, pushed by starlight. The numbers seemed to fit. Its brightness varied tenfold as it tumbled, implying a flat, shiny surface. Its acceleration matched what a lightweight solar sail might experience. Even its trajectory, arriving from the direction of Vega only to swing around the sun like a slingshot, seemed oddly optimized. The scientific backlash was immediate. Mainstream astronomers argued extraordinary claims require extraordinary evidence, and Oumuamua's oddities could still have natural explanations. Maybe it was a shard blown off a Pluto-like exoplanet, rich in nitrogen ice that evaporated invisibly. Or a fractal-like dust iceberg held together by cosmic static. But here's the rub: we'll never know for sure. By the time we spotted Oumuamua, it was already racing away at 95,000 miles per hour, too faint for further study. What lingers isn't just the question of what Oumuamua was, but what it represents. In a galaxy where trillions of similar objects likely wander between stars, how many more will slip through our grasp before we're ready? Future telescopes like the Vera Rubin Observatory promise to catch these interstellar interlopers earlier, giving us time to study or even chase them. Until then, Oumuamua remains a tantalizing Rorschach test against the cosmos, a weirdly shaped ink blot that might be space debris, or someone else's discarded technology tumbling silently into the dark. The Moon today is a silent, barren world with no global magnetic field, but drill into its ancient rocks and you'll uncover a startling secret. Billions of years ago, our closest celestial neighbor crackled with a magnetic force up to 100 times stronger than Earth's is today. How do we know? Apollo astronauts brought back lunar samples hardened in that primordial era, their atoms locked in place like tiny compass needles pointing to a long-lost magnetic past. The puzzle: our current understanding of planetary dynamos says this shouldn't have been possible. A body as small as the Moon, lacking Earth's churning molten core, couldn't sustain such a powerhouse field for long, yet the evidence says it did. The leading theory, the dynamo effect, suggests swirling molten metal in a planet's core generates magnetism, like a cosmic generator. Earth's dynamo thrives thanks to our large molten iron core and rapid spin. But the Moon, it's a fraction of Earth size with a core smaller than the state of California. Even at its birth, heat from its formation should have dissipated too quickly to fuel such a robust field. Some scientists propose a radical solution: gravitational kneading. In the Moon's youth, Earth's tidal forces may have stretched and squeezed its core like putty. creating friction that kept it molten far longer than expected. Others speculate massive asteroid impact stirred the core temporarily, jump-starting short-lived magnetic bursts. Then there's the core crystallization hypothesis. As the moon's molten iron core cooled, lighter elements like sulfur might have risen while heavier iron sank, creating convection currents powerful enough to spin up a dynamo. But here's the twist: lunar magnetism persisted for over 1 billion years before vanishing around 3 billion years ago. That's not a temporary blip, it's a marathon. To explain this, researchers at Rutgers University modeled a scenario where the moon's core acted like a layered cocktail. A solid inner core growing slowly, surrounded by a molten outer layer, with heat radiating unevenly to keep the dynamo churning far longer than physics predicts. The mystery deepens when you consider where the moon's magnetism was strongest. Certain regions, like the Riener Gamma swirl, those eerie, bright patches on the lunar surface, still carry localized magnetic fingerprints, deflecting solar wind like invisible umbrellas. Did the moon's dynamo flicker out unevenly, leaving behind magnetic ghosts, or could these be scars from colossal impacts magnetizing the crust in cataclysmic shocks? What makes this enigma so gripping isn't just the science, it's the stakes. If small rocky worlds can generate strong magnetic fields without Earth-like conditions, exomoons around distant gas giants might harbor protective shields, expanding the hunt for habitable worlds. Meanwhile, NASA's upcoming Lunar Vertex mission plans to land a rover on Riener Gamma in 2024, probing these magnetic anomalies up close. Every new clue peels back layers of the moon's hidden history, reminding us that even familiar worlds guard cosmic secrets, and sometimes the quietest places once roared with celestial fire. When NASA Pioneer 10 and 11 spacecraft raced toward the edges of our solar system, something unexpected happened. They began slowing down more than physics predicted. This tiny but consistent deceleration, just 8.74 times 10 to the negative 10th meters per second squared, became one of space exploration's most perplexing riddles, the Pioneer anomaly. For decades, scientists wrestled with the numbers. The probes were drifting off course by hundreds of thousands of miles, as if an invisible hand was gently pressing the brakes. The discrepancy was small but relentless, accumulating over billions of miles of travel. Even accounting for gravity from the sun and planets, solar wind, and cosmic dust, something wasn't adding up. At first, researchers suspected mundane explanations. Maybe heat radiating unevenly from the probe's nuclear power sources was nudging them off course. Pioneer's design, with its large radio dish pointed back at Earth, meant heat escaping from electronic systems could have acted like a weak photon thruster, pushing against the direction of travel. Simulations showed this thermal recoil could explain some of the anomaly, but not all of it. The numbers still left a stubborn gap, a whisper of something unaccounted for in our understanding of motion through space. Then came the curveball. Missions like New Horizons, which followed similar trajectories decades later, didn't experience the same mysterious drag. If the anomaly was due to some fundamental flaw in our gravity models, why would it only affect the Pioneers? This inconsistency sent theorists down a rabbit hole of possibilities. Could it be evidence of dark matter's gravitational tug in the outer solar system? A sign that Einstein's general relativity needs tweaking at extreme distances. Some even floated the idea of modified inertia, a fringe theory suggesting gravity behaves differently at ultra-low accelerations. The plot thickened when researchers realized earlier spacecraft like Galileo and Ulysses had also shown tiny, unexplained velocity changes, though their trajectories made the data harder to interpret. Was there a hidden variable affecting certain spacecraft designs? A study in 2012 proposed that heat from the Pioneer's electrical systems, reflected asymmetrically off their antennae, might have created just enough thrust to solve the riddle. Later analyses supported this, but skeptics pointed out that even perfect thermal models couldn't fully close the gap. What makes the Pioneer anomaly so fascinating isn't just the unresolved physics, it's the lesson it taught us about humility in exploration. Sometimes the universe hides its secrets in the smallest decimal places, in effect so subtle they're easy to dismiss as noise. And while most scientists now lean toward thermal radiation as the primary culprit, the anomaly's shadow lingers. It reminds us that even our most reliable equations might have blind spots, and that the next great leap in physics could come from a faint, unexplained whisper in the data of an aging spacecraft. Perhaps the real mystery isn't why the pioneers slowed down, but why we're so surprised when the universe refuses to follow our scripts. After all, isn't defiance the essence of discovery? The universe is constantly bombarding Earth with invisible bullets, cosmic rays, particles hurtling through space at nearly the speed of light. Most are protons or atomic nuclei, some carrying energies so immense they make the Large Hadron Collider look like a toy. The real mystery, we have no idea what cosmic powerhouse could launch them. Take the Oh My God particle detected over Utah in 1991. This single proton packed the kinetic energy of a baseball pitch, but compressed into a subatomic speck. Traveling at 0.9999999999996 times light speed, it defied all expectations. According to the Greisen-Zatseping Kuzmin-Gizike cutoff, particles that fast should have been slowed by collisions with cosmic microwave background radiation long before reaching Earth. Yet here it was, screaming through our atmosphere like a rule breaker. The enigma deepens when you trace these rays backward. Their paths twist through interstellar magnetic fields, making pinpointing origins nearly impossible. Some likely come from supernova shocks or active galactic nuclei, where black holes fling matter outward, but the highest energy particles, their potential accelerators, hypernovas. Colliding galaxy clusters remain speculative. Imagine a detective finding a bullet but no gun, no shooter, and no clue how it crossed 10 city blocks without slowing down. Modern observatories like the Pierre Auger Array in Argentina are hunting for answers. With 1,600 water tanks spread over 3,000 square kilometers, it detects the faint glow created when cosmic rays strike the atmosphere. Telescope arrays like Hawk in Mexico peer at gamma rays, hoping to catch secondary clues. Still, the puzzle persists. Some ultra-high-energy rays cluster in suspicious directions, hinting at sources like the nearby Virgo cluster. Others arrive alone, cosmic orphans with no discernible home. What makes this quest so thrilling isn't just the particles, it's what they reveal about the universe's extremes. These aren't just space oddities, they're messengers from regions where gravity and magnetism twist space-time into unrecognizable forms. Every detection is a postcard from the edge of physics, stamped with energies we can't yet replicate. And until we solve their riddles, we're left staring at the sky, wondering what unimaginable forces are firing cosmic bullets at us, and why Earth keeps wound up in the crosshairs. Deep in the swirling myths of space lore, one story has stubbornly clung to the public imagination: the Black Knight satellite. Allegedly an alien probe orbiting Earth for 13,000 years, this phantom object is said to broadcast strange signals, inspired ancient civilizations, and even prompted NASA cover-ups. But peel back the layers, and you'll find a tangled web of misidentified space junk, creative storytelling, and one very real piece of debris that accidentally fueled the legend. The tale begins in 1954, when newspapers reported that a retired Marine Corps pilot named Donald Kehoe claimed the U.S. Air Force had detected two natural satellites orbiting Earth, impossible at the time, since Sputnik wouldn't launch for another 3 years. The story snowballed. By the 1960s, ham radio operators claimed to intercept coded transmissions from an unknown object in polar orbit. conspiracy theorists latched onto grainy photos from early space missions, pointing to dark, irregular shapes they insisted were proof of extraterrestrial technology watching us. The most infamous image, a 1998 NASA STS-88 shuttle mission photo showing a bizarre, tumbling object later revealed to be a thermal blanket lost during an ISS assembly flight. So where did the 13,000-year claim come from? That thread traces back to a misreading of Nikola Tesla's 1920 experiments. Tesla reported intercepting strange radio signals he thought might originate from space, likely misinterpreted natural radio emissions from Jupiter's magnetosphere. Decades later, enthusiasts retroactively linked these reports to the Black Knight myth, weaving together disconnected events into a single narrative. Even the name Black Knight appears to be a modern invention, possibly borrowed from a British rocket program in the 1950s. The reality is far less cinematic, but no less fascinating. Earth's orbit is cluttered with over 27,000 tracked debris objects, from dead satellites to discarded rocket stages. The signals likely came from early satellites like Explorer or even ground-based interference. As for those eerie photos, space is full of oddly shaped debris tumbling in microgravity, reflecting sunlight in ways that defy intuition. The STS-88 thermal blanket, for instance, twisted into a jagged silhouette as it drifted, a perfectly mundane object transformed into an alien artifact through the lens of speculation. Yet the myth persists, fueled by our fascination with the idea that we're not alone, and that evidence might be hiding in plain sight. The Black Knight's endurance reveals less about space and more about us, our love for mystery, our tendency to connect dots where none exist, and the way a single piece of wayward insulation can become a canvas for interstellar dreams. In the end, the real enigma isn't in the sky. It's why we so desperately want these stories to be true. In 1976, NASA Viking 1 orbiter snapped a photograph of the Martian surface that would ignite one of space's most enduring conspiracy theories, the face on Mars. There, in the Cydonia region, stood what appeared to be a massive humanoid visage staring blankly into space, its features eerily symmetrical, stretching nearly 2 miles across with shadows mimicking eyes, a nose, and even lips. The structure looked less like a geological formation and more like something deliberate. Newspapers ran headlines like, "Is someone watching us from Mars?" while UFO enthusiasts proclaimed it proof of an ancient alien civilization. But the real mystery wasn't just the face itself. It was how stubbornly our brains refused to let the illusion go, even as science unraveled it. The phenomenon at play here is pareidolia, the human tendency to perceive meaningful shapes in random patterns. We see faces in clouds, animals in rock formations, even religious figures in toast. It's a survival mechanism hardwired into our brains to help us quickly recognize predators or allies. Mars, with its wind-sculpted mesas and eroded cliffs, is a pareidolia playground. The face was never more than a trick of light and angle, a mesa tilted just right to cast shadows that mimicked facial features when the sun hit it at 35 degrees. But when the image hit the public, low resolution and grainy, it was a Rorschach test for the imagination. NASA scientists knew better. They captioned the original press release with a dry explanation. The huge rock formation resembles a human head. But by then, the myth had taken flight. Books like Richard Hoagland's The Monuments of Mars spun elaborate tales of a lost Martian civilization, linking the face to nearby pyramids and ruined cities. When later missions like Mars Global Surveyor and Mars Reconnaissance Orbiter returned high-resolution images in the late 1990s and 2000s, the truth was undeniable. The face was just a hill, its features smoothed out into unremarkable slopes under clearer lighting. Yet here's the twist: even after debunking, the face refused to fade. Some claimed NASA was hiding sharper images, or that the real face lay buried beneath dust. Others pointed to newer photos, insisting shadows still hinted at artificiality. The conspiracy evolved, arguing that if the face was natural, its placement near other structures couldn't be coincidence. Psychologists call this backfire effect when confronted with evidence against a belief. Some cling harder to it. The face became a cultural touchstone, inspiring episodes of The X-Files, sci-fi novels, and endless internet forums. What makes this mystery so captivating isn't the rock itself, but what it reveals about us. Mars holds countless mesas, but we fixated on the one that looked back. In a way, the face did exactly what we imagined it watched, not from space, but from the mirror of our own psychology. Every grainy photo, every conspiracy theory, was a testament to humanity's hunger for connection in the cosmos. The real Enigma was never on Mars. It was why we so badly wanted the face to be real, and what that says about our lonely place in the universe. Saturn's North Pole holds a secret so geometrically perfect. It looks like nature drafted it with a protractor, a colossal hexagon, wider than two Earths, spinning in eerie synchrony with the planet's rotation. This six-sided storm, first glimpsed by Voyager in the 1980s and later studied in stunning detail by Cassini, defies everything we know about fluid dynamics. Hurricanes on Earth are chaotic spirals. Jupiter's great red spot is a swirling oval, but Saturn's hexagon, its razor-sharp angles and near-mathematical precision suggest something far stranger at work. The sheer scale is staggering. Each side spans nearly 9,000 miles, with winds screaming at 320 miles per hour, enough to fling debris from one edge to another like cosmic shrapnel. Yet despite this violence, the hexagon's structure remains freakishly stable, maintaining its shape for at least 4 decades and likely much longer. When Cassini's infrared cameras pierced Saturn's hazy atmosphere, they revealed the hexagon plunging 60 miles deep, a towering, honeycomb-colored vortex locked in place like a celestial bolt. Lab experiments have tried and failed to recreate this phenomenon. In 2010, Oxford physicists spun a 30-liter drum of water, injecting dye to visualize flow patterns. At certain speeds, they produced fleeting polygons, including a hexagon, but their shapes dissolved within minutes, whereas Saturn's has outlasted generations of scientists. The key difference: scale and rotation. Saturn spins every 10.5 hours, faster than Earth but slower than Jupiter, while its atmospheric layers shear against each other like nested gears. Some theorists propose this creates standing waves. Think of vibrations in a guitar string that freeze the storm's edges into geometric rigidity. Others point to the planet's deep jet streams, which may act like invisible walls corralling the chaos. Cassini's most haunting discovery was the hexagon's seasonal heartbeat. As Saturn's North Pole tilted toward the Sun during its 7-year summer, the storm's high-altitude haze warmed, turning from blue gold to a smoggy yellow. Yet the hexagon itself remained unchanged, a silent sentinel beneath the shifting light. Even more puzzling, the South Pole hosts no such structure, just a conventional cyclone. Why does symmetry reign only at one pole? The hexagon's persistence taunts us with a fundamental truth. The universe adores patterns, but it rarely follows our textbooks. Whether it's deep-rooted physics we haven't decoded or some alien elegance in turbulence we've yet to imagine, this storm is more than a curiosity. It's a masterclass in celestial geometry, etched into the clouds of a gas giant. And until we crack its code, Saturn will keep spinning its perfect enigma, 6 sides and all. Somewhere in the constellation Bootes lies a cosmic nightmare, a yawning chasm so vast it defies comprehension. The Bootes void, spanning 330 million light-years, isn't just empty, it's aggressively empty. Imagine tearing a hole in the universe's fabric where nothing exists: no galaxies, no stars, not even the faint glow of wandering gas clouds. If the Milky Way were placed here, astronomers of neighboring galaxies wouldn't have known we existed until the 1960s, when telescopes finally peered far enough to spot us. This isn't a mere gap, it's a gravitational graveyard, a place where the universe forgot to build anything at all. The void's discovery in 1981 shattered expectations. Large-scale surveys like the Sloan Digital Sky Survey expect space to resemble a cosmic web. Filaments of galaxies woven around bubble-like voids, but Boots isn't a bubble, it's a bottomless pit. While typical voids span 100 million light-years, Boots is 3 times that size and contains only 60 galaxies. To put that in perspective, a region that size should host around 2,000. The handful of galaxies trapped inside huddle together like survivors on a life raft, drifting through an ocean of nothingness. What carved this abyss? One theory points to dark flow, an eerie phenomenon where galaxy clusters stream toward a single point beyond the observable universe like leaves caught in a cosmic current. Some suggest the Boots void could be the fingerprint of a collision with another universe during inflation, leaving behind a scar of absolute emptiness. Others propose it's evidence of an ancient, hyper-advanced civilization that somehow harvested every scrap of matter, though physicists quickly note that even a Kardashev Type 3 civilization would lack the energy to pull off such cosmic archaeology. But the most unsettling possibility, the void might expose flaws in our cosmology's bedrock. The Big Bang predicts matter should distribute somewhat evenly, like raisins in rising dough. Boots isn't just uneven, it's a missing bite. Could quantum fluctuations during inflation have left behind such extreme voids? Or does dark energy work differently here, repelling matter so fiercely it created a desert vaster than any model allows? Every telescope trained on Boots finds only more questions. The galaxies inside show no signs of trauma, they're not fleeing the void, which rules out some explosive origin. Their stars burn normally, as if unaware they're floating in a cosmic anomaly. Meanwhile, the void's edges are suspiciously sharp, like a knife cut through the universe's tapestry. What makes Boots so haunting isn't just its emptiness, it's the silence. In a cosmos teeming with light and motion, this void is a blank page in the middle of a thrilling novel. It dares us to admit how little we understand about the universe's structure and whispers that some mysteries might be too vast to solve. After all, how do you study nothing when nothing is all there is? Look up at the night sky just before dawn or after dusk, and you might catch an eerie, faint glow stretching upward from the horizon. A luminous pyramid of light often mistaken for twilight's last gasp. This is the zodiacal light, a cosmic mystery hiding in plain sight. For centuries, poets and astronomers puzzled over its soft radiance, attributing it to everything from atmospheric anomalies to celestial fires. Today, we know it's sunlight reflecting off trillions of dust particles swirling around the inner solar system. But that answer only cracks the door to a deeper enigma. These particles form a vast, pancake-shaped cloud along the ecliptic plane, the same path planets follow around the Sun. You'd expect this dust to be evenly distributed, thinning gently as you move outward from the Sun. Yet the zodiacal light flares brighter beyond Mercury's orbit, defying predictions. Some regions gleam like dirty glass catching sunlight, while others appear suspiciously dim. The contradiction gnaws at scientists. If the dust comes from asteroid collisions and comet tails, as most theories suggest, why doesn't it spread uniformly? The leading suspect, catastrophic smash-ups. When asteroids collide, they don't just chip, they explode into powdery debris. Simulations show a single giant collision, like the one that created the Charon asteroid family 80 million years ago, could have dumped enough dust to temporarily double the zodiacal light. But these events are rare and the glow persists. That's where comets come in. As icy wanderers like Halley or Encke swing close to the Sun, they shed glittering trails of dust like cosmic breadcrumbs. The European Space Agency's Rosetta mission even caught Comet 67P coughing out thousands of dust grains daily. Here's the twist: the dust shouldn't last. Solar radiation should push smaller particles outward, while the sun's gravity tugs larger ones inward in a spiral of destruction. Yet the zodiacal light's stability suggests a constant replenishment, a conveyor belt of destruction and renewal. Could unseen asteroid clusters be grinding themselves to dust? Are dark comets stealthy ice balls cloaked in dust, secretly feeding the cloud? The mystery deepens when you peer beyond our solar system. Other stars show similar dust disks, but theirs often appear warped or clumpy, sculpted by unseen planets. Does our zodiacal light hide similar secrets? NASA's upcoming James Webb Space Telescope aims to find out, mapping the dust structure in infrared. Maybe then we'll learn whether we're seeing the ghostly aftermath of ancient collisions or the quiet stirrings of something stranger. For now, the zodiacal light remains a celestial whisper, a reminder that even the space between planets isn't truly empty, but alive with drifting, dancing dust, each grain a tiny puzzle waiting to be solved. Beyond the orbit of Neptune, the solar system doesn't fade gently into darkness, it plunges. Around 50 astronomical units out, something bizarre happens. The Kuiper Belt, that icy debris field of leftover planet-building material, suddenly stops dead. It's called the Kuiper Cliff, and this cosmic drop-off is so abrupt, it's as if someone drew a line in the solar system's backyard and declared, nothing past this point. The strangest part, we have no idea why. For decades, astronomers assumed the Kuiper Belt extended smoothly to at least 150°, thinning gradually like sand at the edge of a desert. Then telescopes started counting. Beyond 50°, the number of detectable objects doesn't just dwindle, it crashes. Only a handful of icy bodies like Sedna and far, far out drift beyond this invisible boundary, lonely wanderers in a region that should be bustling with frozen relics. The math is unequivocal. This isn't a natural distribution. Something either swept the area clean long ago or is hiding in the shadows, warping the landscape with unseen gravity. Enter the Planet 9 hypothesis. In 2016, Caltech astronomers Konstantin Batygin and Mike Brown noticed that several extreme trans-Neptunian objects shared bizarre, clustered orbits tilted away from the solar plane. Their simulations showed a massive, undiscovered world 10 times Earth's mass, orbiting some 500° out, could shepherd these orbits and carve the Kuiper Cliff. The idea ignited both excitement and skepticism. Could a planet that big really lurk undetected? The math suggests yes. At that distance, even Jupiter-sized objects would reflect too little sunlight for current surveys to spot. The Vera Rubin Observatory, coming online soon, may finally settle the debate, but alternative explanations abound. Some argue the cliff is an illusion, a consequence of observational bias where distant, dark objects simply vanish from telescope sight. Yet, even accounting for detection limits, the drop-off remains statistically jarring. Others propose ancient upheaval. Perhaps Neptune's outward migration during the solar system's youth flung most Kuiper Belt objects inward, leaving the outer realm barren. There's just one problem: models show this migration would have left a smoother gradient, not a cliff edge. Then there's the wild card: passing stars. Billions of years ago, when the Sun was born in a dense stellar cluster, close encounters with sibling stars might have ripped away the outer Kuiper Belt like tidal theft. Recent simulations show a star grazing within 800° could have done the job, stealing our solar system's icy fringe and leaving behind the cliff we see today. What makes this mystery so captivating isn't just the unanswered question, it's the audacity of the possibilities. The Kuiper Cliff forces us to confront how little we know about our own cosmic neighborhood. Is it the fingerprint of a hidden world, a relic of stellar burglary, or something entirely unforeseen? Until we peer deeper into the dark, the edge of the solar system remains a frontier of pure speculation and the perfect setting for the next great discovery. The universe has a missing matter problem, but not the kind you might think. While dark matter steals the spotlight, ordinary matter, the stuff that makes up stars, planets, and even us, has its own vanishing act. Scientists call this the missing baryon problem, and it's one of cosmology's most frustrating accounting errors. Here's the puzzle. If you tally all the normal matter we can see, galaxies, gas clouds, everything glowing in telescopes, it adds up to barely half of what the Big Bang's leftover radiation says should exist. Where's the rest? The answer might lie in threads of ghostly gas so hot and diffuse they're practically invisible, or in black holes slurping matter into oblivion before we can spot it. Meet the WIM, the warm, hot intergalactic medium. Picture a cosmic spiderweb, its strands stretching between galaxies, filled with gas heated to millions of degrees but spread so thin, a cubic meter might hold just a few atoms. This isn't empty space, it's matter in hiding. At these temperatures, hydrogen and helium atoms get stripped of electrons, becoming ionized plasma that barely emits light. To detect it, astronomers turn to nature's backlight, distant quasars. As these ultra-bright galactic cores beam light across the universe, the WIM ions snatch specific wavelengths, leaving faint absorption lines in the quasar's spectrum like fingerprints on a window. The challenge: these signals are whispers in a hurricane. Only the most sensitive telescopes like the Chandra X-ray Observatory can tease them out, and even then only for the densest filaments. Then there's the black hole angle. Some theorists suggest a portion of the missing matter might have plunged into intermediate mass black holes, the elusive middleweights between stellar black holes and supermassive giants. These cosmic traps could have swallowed gas and stars without the dramatic fireworks that reveal their presence. The trouble is proving it. Unlike their supermassive cousins, which light up galactic centers, these stealthy black holes leave few traces unless they're actively feeding. Enter fast radio bursts, the universe's accidental detectives. These millisecond-long cosmic screams travel billions of light years, and their waves get slightly slowed by electrons in intervening matter. By measuring how much an FRB's signal disperses, astronomers can estimate how much stuff it passed through. Recent studies using FRBs like the repeating 2012-11-2 found more electrons along their paths than visible matter accounts for, hinting at hidden baryons in the WIM-tangled filaments. The hunt isn't just academic. Solving this riddle could reshape our understanding of cosmic structure. Those invisible baryons might be the glue holding galaxy clusters together, or the reservoir fueling future star formation. And if black holes are the culprits, their numbers could rewrite theories of galactic evolution. For now, the missing baryons remain a cosmic game of hide and seek, played across the vast distances between galaxies, where matter isn't truly lost, just waiting for us to decode its hiding places. The cosmic microwave background, that ancient afterglow of the Big Bang, should be the universe's most democratic feature, a frozen snapshot of infancy where no direction is special. Yet when scientists mapped its subtle temperature variations, they stumbled upon something that made them question everything. Dubbed the axis of evil, this bizarre pattern shows the CMB's fluctuations appear suspiciously aligned with both the plane of our solar system and our galaxy's orientation. It's as if the universe left a fingerprint and it's pointing right at us. The discovery first rattled cosmologists in 2005, when data from NASA WMAP satellite revealed an unexpected asymmetry. The CMB's hot and cold spots weren't scattered randomly. They seemed to organize along a preferred axis that weirdly coincides with our ecliptic plane. Later measurements by the Planck spacecraft only deepened the mystery. The odds of this happening by chance, less than 1 in 10,000. Some researchers dismissed it as a fluke, an artifact of measurement errors or foreground interference. But when independent teams accounting for every possible bias kept finding the same alignment, the discomfort grew. At stake is one of cosmology's sacred cows, the Copernican principle, which states we don't occupy a privileged place in the universe. The axis of evil's alignment with our solar system feels unsettlingly personal. Could there be some unknown local contamination skewing the data, the Milky Way's dust or the sun's magnetic field distorting the signal? Efforts to purge these influences still leave a stubborn residue of alignment. That's when theories got radical. One camp suggests this might be evidence of a pre-Big Bang universe, a cosmic bruise from a collision with another space-time bubble during inflation. Others propose our universe is finite and strangely shaped, like a hall of mirrors where light wraps around, creating phantom patterns, the wildest idea. That we're seeing quantum entanglement imprinted at the universe's birth, linking the CMB's structure to our local geometry in ways physics can't yet explain. Skeptics counter that humans excel at finding patterns where none exist, a cosmic Rorschach test gone awry. They point to the look elsewhere effect. With trillions of potential correlations in the data, something was bound to line up by accident. But as Planck's final data release showed, the axis of evil refuses to vanish under scrutiny. It lingers, a celestial uninvited guest at the grand banquet of cosmology. What makes this mystery so tantalizing isn't just the potential rewrite of cosmic history, it's the philosophical vertigo. Either we've stumbled upon a statistical ghost, or the universe is whispering that we are special after all. And for a species raised on the mantra of cosmic mediocrity, that's the most unsettling possibility of all. Amid the chaotic beauty of nebulae, those swirling stellar nurseries and supernova remnants, one structure stands out for its eerie precision: the red rectangle. Floating about 2,300 light-years away in the constellation Monoceros, this cosmic gem looks less like a cloud of gas and more like a stained glass window designed by a mathematician. Its nested, ladder-like rungs of glowing dust form a near-perfect X shape, encased in a rectangular halo so symmetrical it seems impossible. But here's the twist: this isn't some alien art project. It's the death throes of a binary star system, a celestial dance that should create messy, asymmetrical outflows, not geometry textbook perfection. The story begins with HD 44179, the aging star pair at the nebula's heart. As the primary star puffed off its outer layers, its companion star, orbiting unusually close, should have twisted those ejections into spirals or clumps. Instead, we get a series of near-identical concentric rings, their edges razor-sharp, as if shaped by invisible cosmic stencils. Hubble's close-ups reveal even finer details: twin jets of material shooting from the poles, threading through the X like taut wires, while the rectangle's corners glow with unnatural crispness. The whole structure defies the usual rules of stellar winds and turbulence, where chaos should reign. So how does nature craft such precision? One clue lies in the nebula's bizarre chemistry. Unlike most nebulae rich in hydrogen and helium, the red rectangle is packed with complex carbon molecules like anthracene and pyrene, building blocks of life forged in the star's death throes. These hydrocarbons might act like cosmic scaffolding, organizing the outflow into rigid shapes as they condense into dust. Imagine blowing smoke through a sieve. The carbon compounds could be filtering the chaos into orderly lane. Then there's the timing. The rectangle's symmetry suggests the binary star's orbits are perfectly synchronized with the ejection rate, like a spinning top releasing material at just the right intervals to build geometric layers. Simulations show that if the star's dance is too precise, their gravitational tug of war can mold escaping gas into cones, which, viewed edge-on, appear as an X. But even this doesn't fully explain the rectangle's sharp borders or the ladder's uniform spacing, features more reminiscent of crystal growth than stellar winds. The real kicker: the red rectangle isn't alone. Recent discoveries have spotted similar geometric nebulae like the blue snowball and the diamond ring, each with their own weirdly angular shapes. Could there be an entire class of polygonal planetary nebulae we've overlooked? And if so, what hidden physics governs their formation? Some theorists wonder if magnetic fields, usually too weak to shape nebulae on large scales, might play an outsized role here, combing the dust into alignment like iron filings near a magnet. What makes this cosmic quilt so mesmerizing isn't just its beauty, it's the defiance. In a universe where entropy rules, where gas and dust should scatter randomly, the red rectangle stands as a quiet rebel. Its perfect angles whisper that there's still so much we don't understand about how stars die, and how sometimes their final act isn't a chaotic explosion, but a carefully folded farewell. Our galaxy isn't just a peaceful island of stars. It's a cosmic predator, and right now, it's in the middle of a slow-motion feast. The victim, the Sagittarius dwarf galaxy, a tiny neighbor that's been torn apart over billions of years, its stars stretched into shimmering loops around the Milky Way like celestial spaghetti. But here's the twist. As astronomers trace the carnage, they've stumbled upon something that shouldn't exist. The dark matter halo surrounding this dwarf galaxy isn't behaving like it's supposed to, and that anomaly might rewrite everything we thought we knew about how galaxies grow. The saga began in 1994 when astronomers discovered Sagittarius lurking just 50,000 light-years from Earth, hidden behind the Milky Way's dense star fields. At first glance, it seemed unremarkable, a faint smudge of stars 10,000 times lighter than our galaxy. But as telescopes pierced the dust, a breathtaking sight emerged, not a tidy dwarf galaxy, but a shredded corpse. The Milky Way's gravity had ripped Sagittarius apart, scattering its stars into vast, looping streams that wrap around our galaxy like ribbons. One stream arcs high above the galactic plane, another dives below, tracing a polar orbit so extreme it defies expectations. These tidal tails aren't just debris, they're a fossil record of the Milky Way's appetite, a slow-motion replay of galactic digestion. Yet the real shock came when scientists mapped Sagittarius's dark matter. Dwarf galaxies are supposed to be encased in massive, puffy halos of this invisible stuff, which acts like gravitational glue holding their stars together. But Sagittarius's halo is weirdly deflated. As the Milky Way stripped away stars, the dark matter didn't follow the script. It's either being stripped far more efficiently than models predict, or it wasn't there in the first place. This throws a wrench into the standard, bottom-up theory of galaxy formation, where big galaxies grow by swallowing smaller ones packed with dark matter. If Sagittarius is any indication, dwarf galaxies might be lighter, weirder, and less dark matter-rich than we assumed. The plot thickens when you examine the stars themselves. Most galactic mergers scatter stars randomly, but Sagittarius's loops are oddly organized. Some clump in unexpected places, like the Virgo overdensity, a mysterious swarm of stars above the Milky Way's disk that might be a chunk of Sagittarius flung far beyond the mainstreams. Others orbit backward against the Milky Way's rotation, as if the dwarf galaxy came in at a bizarre angle. Simulations suggest this chaos isn't from a single collision but multiple close passes over billions of years, each yanking stars into new, ever-stranger trajectories. But the most tantalizing clue lies in the metal-poor star Sagittarius, brought with it ancient relics from the early universe, rich in elements like europium but lacking heavier metals like iron. These stars shouldn't exist in a tiny dwarf galaxy, which lacks the supernova firepower to forge such exotic chemistry, unless Sagittarius wasn't always small. Some astronomers now suspect it was once a much larger galaxy, stripped down to its core by repeated encounters with the Milky Way. Its unusual stars might be survivors from that lost golden age, cosmic refugees carrying secrets of a brighter past. What makes this celestial demolition so fascinating isn't just the violence, it's the unanswered questions. Why is dark matter evacuating the sinking ship faster than stars? How did Sagittarius retain its weirdly coherent loops despite being torn apart? And could its demise explain other Milky Way oddities, like the strangely young stars in our galaxy's outer reaches? Every new survey, from Gaia's star maps to Vera Rubin's upcoming deep scans, peels back another layer. One thing's certain, the Milky Way isn't just a peaceful spiral. It's a cannibal, and Sagittarius is the proof staining its cosmic teeth. In the vast tapestry of galaxies, most fall into familiar shaped spirals with their graceful arms, ellipticals like glowing orbs, or messy irregulars caught in mid-collision. Then there's Hoag's object, a cosmic bullseye so perfect it looks photoshopped. Discovered in 1950 by astronomer Arthur Hoag, this ring galaxy floats 300 million light-years away in the constellation Serpens, its golden core encircled by a dazzling blue ring of newborn stars, separated by a yawning gap of near-total darkness. No spiral arms, no connecting bars, just a pristine circle hanging in space like a celestial halo, and it breaks every rule we know about how galaxies grow. Typical ring galaxies, like the cartwheel, form through violent collisions. When a smaller galaxy punches through a larger one's center, the shockwave triggers star formation in a rippling ring. But Hoag's object shows no signs of trauma. Its core is eerily calm, no warped dust lanes, no stellar debris hinting at a past crash. The ring orbits almost perfectly aligned, its stars twinkling in uncanny symmetry. Even stranger, the gap between core and ring is almost empty, a no-man's land spanning tens of thousands of light-years where nothing stirs. It's as if someone carved the galaxy with celestial precision, leaving only the recipe's ingredients: old stars in the center, young ones at the edges, and void in between. Theories swirl like dust in a cosmic wind. One camp suggests a secular evolution scenario where internal processes, maybe gas settling into waves, slowly built the ring over billions of years. Others propose a long-ago merger so gentle it left no scars, like a pebble dropped into a pond creating smooth ripples instead of splashes. Then there's the rogue idea, a phenomenon called bar instability, where a galaxy's central bar common in spirals spontaneously dissolves, flinging stars outward into a ring. But Hoag's object never had a bar to begin with, leaving astronomers chasing shadows. The plot thickens when you peer deeper. Hubble images reveal a second, fainter ring nestled inside the first, like a nesting doll's hidden layer. Even more baffling, a background galaxy visible through Hoag's gap hints this might not be a one-off wonder. It could belong to an ultra-rare subclass of galaxies that evolved in isolation, untouched by the chaos shaping their peers. What makes Hoag's object so mesmerizing isn't just its beauty, it's the defiance. In a universe where gravity sculpts chaos, here's a galaxy that chose perfect geometry. Every unanswered question, how it formed, why it persists, whether more like it lurk undetected, challenges our galactic origin story. Until we solve its riddle, Hoag's object remains a cosmic Ouroboros, a snake eating its tail, whispering that the universe's greatest artworks might also be its most mysterious. Most triple star systems follow predictable rhythms, like a cosmic waltz where gravity's rules dictate every step. Then there's KIC 28569660, a trio of stars that defies every model astronomers throw at it. Discovered by NASA Kepler telescope, this system should be straightforward. Two stars orbiting closely while a third dances farther out, but their light curves, the dips in brightness as they eclipse each other, reveal a pattern so chaotic it's left scientists staring at their screens in disbelief. The math says these stars can't move the way they do. Their orbits twist into knots that physics insists should unravel instantly, yet somehow, against all odds, they persist. Kepler spotted the first puzzle back in 2011. The system's light dimmed in sharp, overlapping patterns suggesting three stars, two smaller ones locked in a tight embrace, eclipsing each other every 24 hours, while a third, larger star passed in front of them every 200 days. So far, so normal, but when researchers tried to simulate the orbits, the numbers revolted. No matter how they tweaked the variables, masses, distances, inclinations, the system collapsed into nonsense within a few simulated years. The slightest adjustment sent stars careening into each other or flinging one another into the void. Reality, however, showed KIC 28569660 humming along perfectly, its eclipses ticking with clockwork precision. Theories piled up like desperate Hail Marys. Maybe a fourth star lurked unseen, adding gravitational chaos to the mix. Nope, additional searches found no trace. Could the stars be precessing, their orbits wobbling like spinning tops? Calculations suggested that effect would be too weak to explain the anomalies. Some even proposed wild card ideas, like one star being a black hole stealthily warping the other's paths. But black holes don't eclipse light, and Kepler's data showed all three stars passing in front of each other. The most promising lead came from hierarchical models, where the two inner stars orbit so close they act like a single object to the outer star. Yet even this elegant solution crumbled. The math still couldn't replicate the system's eerie stability. What makes this celestial riddle so maddening isn't just the failed models, it's the implications. If three stars can defy our best simulations, what else might we be missing? Could other impossible systems hide in plain sight, their secrets buried in Kepler's archived data? The mystery of KSE 28566960 lingers like a cosmic koan, challenging us to admit how much we still don't understand about gravity's ballet. Until we crack its code, it stands as a glittering reminder. Even the universe's most ordinary-looking corners can harbor jaw-dropping defiance. Hidden in the constellation Monoceros, the unicorn lurks an object so small it defies classification. Dubbed the unicorn, this cosmic oddity weighs just 3 times the mass of our Sun, cramming all that matter into a space smaller than Manhattan. That puts it smack in the mass gap, a controversial no-man's land between neutron stars and black holes where astrophysics textbooks say nothing should exist. The unicorn isn't just challenging what we know about stellar corpses, it's tearing up the rulebook entirely. Most black holes we've found are either stellar mass remnants, born when massive stars collapse, typically 5 to 15 times the Sun's mass, or supermassive behemoths anchoring galaxies. Neutron stars, meanwhile, cap out around 2.2 solar masses any heavier, and they should collapse into black holes. The gap between those extremes has long been considered a forbidden zone, governed by the brutal physics of stellar death. But the unicorn, discovered in 2021 through its gravitational tug on a neighboring red giant, sits precisely in that theoretical dead zone. Its very existence forces astronomers to ask, is this a featherweight black hole rewriting the rules, or a neutron star masquerading as something darker? The debate hinges on a cosmic balancing act. Neutron stars resist collapse through neutron degeneracy pressure, a quantum effect where packed neutrons push back against gravity like an overstuffed suitcase. But cross that critical mass threshold, and even neutrons can't hold the line. The unicorn's 3 solar mass weight should have doomed it to black hole status, except it's not behaving like one. Unlike black holes, which betray their presence through X-rays as they devour matter, the unicorn's companion star shows no signs of being cannibalized. Instead, the red giant's light dims and brightens in sync with an unseen object's orbit, a subtlety more characteristic of a neutron star's gentle gravitation. Skeptics argue the unicorn could be an unusually dense neutron star, its heft inflated by measurement errors or exotic internal physics. Some theories suggest ultra-dense, strange stars, made of quark-gluon plasma rather than neutrons, could sneak into the mass gap. Others propose the object might be a binary neutron star caught mid-merger, its combined mass temporarily blurring the line between star and singularity. But supporters of the black hole hypothesis point to the star's warped shape stretched like taffy by something compact enough to be a black hole's event horizon. The stakes go beyond one weird object. If the unicorn is a black hole, it implies the mass gap isn't empty, just poorly explored. Current detection methods favor heavier black holes or bright neutron stars, leaving puny, dark holes like this nearly invisible. Future gravitational wave detectors could settle the debate by listening for the unicorn's ring down, the space-time vibrations emitted when black holes form. Until then, this celestial unicorn remains a riddle wrapped in a mystery, grazing quietly in a theoretical pasture we're only beginning to map. And whether it's a neutron star in a monster's clothing or a black hole that slipped through the cracks, one thing's certain: the universe loves throwing curveballs, especially when we least expect them. Beneath Europa's icy crust, an ocean wider than Earth's own Pacific churns, yet its tides rise and fall in ways that defy every prediction. Scientists expected Jupiter's gravitational tug to create predictable swells in this hidden sea, but the actual measurements left them stunned. The tides are smaller than they should be, somewhere between 30 to 65 feet high, when models insisted they'd tower over 300. It's as if the laws of physics play by different rules under Europa's frozen shell, and the implications could rewrite our understanding of alien oceans. The puzzle begins with Jupiter's relentless pull. Europa orbits the gas giant in an elliptical path, stretching and compressing like a cosmic stress ball. This flexing should generate intense tidal forces, heating the moon's interior through friction and creating massive ocean swells. Yet radar and magnetic field data from spacecraft like Galileo reveal a dissonance. The tides exist, but they're suspiciously subdued. One theory suggests Europa's icy shell isn't rigid, as once assumed, but floats atop the ocean like a loose lid, absorbing some of the tidal energy before it can fully transfer to the water below. Imagine shaking a snow globe only to find the glitter inside moves sluggishly because the glass itself is bending. Then there's the ocean's chemistry. If Europa's waters are laced with salts like magnesium sulfate, a possibility hinted at by surface discoloration, their viscosity might dampen tidal motion. Think of the difference between sloshing water in a bowl versus thick syrup. The latter resists forming high waves, but even this explanation falls short. Simulations show salinity alone can't account for the drastic discrepancy. That's when researchers turn to the seafloor itself. What if Europa's ocean isn't just sitting still? Hydrothermal vents, like those on Earth's mid-ocean ridges, could be stirring the waters with heat and currents, redistributing energy in ways that suppress large-scale tides. These vents might also explain another enigma: Europa's surface fractures, which spew plumes of water vapor into space. If the ocean is actively venting, it's not just a passive pool, it's a dynamic system, possibly even hiding life-friendly niches. The wild card, Europa's core. Some models propose its metallic heart generates a weak magnetic field, interacting with Jupiter's own to create subsurface electromagnetic forces that subtly break the tides. Others speculate the ocean isn't uniform but layered, with zones of varying density acting like underwater speed bumps. Every hypothesis leads back to the same startling possibility: Europa's ocean isn't just a featureless void. It's a labyrinth of hidden structures, currents, and energies we're only beginning to fathom. Upcoming missions like NASA Europa Clipper aim to pierce this mystery with ice-penetrating radar and gravity measurements. But for now, Europa's phantom tides remain a tantalizing riddle, a reminder that even in our solar system's backyard, the deepest secrets don't always make the biggest waves. The James Webb Space Telescope was supposed to clarify the universe's infancy, but instead it handed scientists a paradox wrapped in starlight. Deep in its first images, JWST spotted galaxies so massive, so mature, they shouldn't exist. These cosmic behemoths, glimpsed a mere 300 million years after the Big Bang, flaunt hundreds of billions of stars packed into structured disks and spirals, as if the universe hit fast forward on galaxy formation. According to conventional models, such colossal structures needed billions of years to assemble. Their existence isn't just surprising, it's a direct challenge to cosmology's foundational timeline, forcing astronomers to question whether we've misunderstood dark matter, gravity, or even the Big Bang itself. Take galaxy JWST 14-0, shining from the universe's toddler years at just 290 million years old. Its light reveals a stellar population weighing several hundred million suns. a respectable size for a modern galaxy, let alone one from an era when the cosmos was 2% its current age. Even stranger, its stars aren't just old, they're metal-rich, meaning previous generations had already lived, died, and seeded space with heavy elements. This implies an impossibly rapid cycle of star birth and death, crammed into a window too narrow for standard physics. Simulations suggest such galaxies needed at least 750 million years to form. But JWST data says they were already polished gems before the universe finished its first cosmic coffee. The implications ripple across astronomy. One radical solution tosses out dark matter entirely, proposing modified gravity as the culprit. If gravity behaves differently on cosmic scales, maybe galaxies could clump together faster. But struggles to explain other JWST observations, like perfectly formed galactic disks that shouldn't stabilize without dark matter's scaffolding. Another camp suggests these impossible galaxies are cosmic illusions lensed or magnified by foreground objects. Yet JWST follow-up spectroscopy confirms their distances, leaving no room for tricks. Then there's the dark matter twist. If these early galaxies did form around ultra-dense dark matter halos, their sheer brightness implies star formation rates 100 times fiercer than in modern galaxies. Picture a million supernova detonating in synchrony, their shockwaves compressing gas into new stars at breakneck speed. Yet even this extreme scenario barely reconciles the timeline. Some theorists whisper about primordial black holes, ancient singularities left over from the Big Bang, seeding galaxy growth before stars even ignited. Others propose a cyclical universe where these impossible galaxies are actually recycled relics from a previous cosmic iteration. What makes this mystery so electrifying isn't just the scientific upheaval, it's the raw audacity of the cosmos. Every new JWST image peels back another layer of the early universe, revealing not the hazy, chaotic nursery we expected, but a polished gallery of mature islands floating in the dark. Whether the answer lies in revised physics, unseen forces, or something entirely unforeseen, one thing's clear: the universe's opening chapters were far stranger, far more brilliant than we ever dared imagine. And the deeper we look, the more the past refuses to follow the rules. Venus might be Earth's twin in size, but its atmosphere is a nightmare version of our own, a crushing, acid-laden maelstrom where temperatures melt lead and winds scream at hurricane force. Yet even in this hellscape, nothing is more baffling than the spinning monstrosity parked at its south pole. A double-eyed vortex so bizarre, it makes earthly hurricanes look like gentle breezes. First spotted by Europe's Venus Express orbiter in 2006, this storm isn't just a swirling mass of clouds, it's a shape-shifting enigma, morphing from a figure 8 to a pair of nested funnels in mere hours, defying every atmospheric model we throw at it. The storm's anatomy is unlike anything in our solar system. At its core, two distinct eyes of calm rotate around each other like celestial dancers, each spanning over 1,200 miles, wide enough to swallow Texas whole. Surrounding them, a churning collar of sulfuric acid clouds races at 200 miles per hour, completing a full revolution every 2.5 Earth days. But here's the twist: unlike Jupiter's Great Red Spot or Earth's hurricanes, which cling stubbornly to predictable paths, the Venusian vortex meanders erratically. Some days it drifts lazily around the pole, others it jerks abruptly, as if yanked by invisible strings. Thermal cameras reveal even weirder details. The vortex isn't flat but a towering funnel stretching 30 miles high, with temperature swings of 80 degrees Fahrenheit between its rim and core. Scientists initially assumed the vortex was a simple side effect of Venus's superrotation, where the entire atmosphere circles the planet 60 times faster than its surface. On paper, polar vortices should form as fast-moving equatorial winds collide and spiral poleward, like water draining from a bathtub. But simulations can't replicate the vortex's split personality. Earth's hurricanes draw energy from warm ocean waters, yet Venus has no oceans, just a blistering surface hot enough to vaporize organic compounds. Some theories suggest thermal tides, atmospheric waves triggered by solar heating might pump energy into the storm. Others point to mysterious gravity waves, not to be confused with gravitational waves rippling through Venus's thick air, potentially twisting the vortex into its double-lobed form. The real shock came when Japan's Akatsuki probe arrived in 2015. Its infrared eyes caught the vortex doing something unprecedented, sprouting a colossal, snake-like filament that stretched halfway across the planet before dissolving into the chaos. This tendril of cold gas, over 6,000 miles long, behaved like nothing in any atmospheric textbook. Was it a rogue jet stream, the aftermath of a colossal atmospheric collision? Even the most sophisticated algorithms can't stabilize the vortex's shape for more than a few simulated days before it unravels into digital noise. What makes this tempest so mesmerizing isn't just its defiance of physics, it's the window it offers into alien meteorology. Venus's vortex is a laboratory for extremes where familiar forces play out in terrifyingly unfamiliar ways. As NASA Da Vinci and Veritas missions prepare to probe Venus's secrets in the next decade, one thing's certain: this isn't just a storm. It's a swirling cipher, a whirlwind of unanswered questions, and the more we stare into its twin eyes, the more they stare back, unblinking, from the heart of a planetary enigma. Mars has been teasing us with a ghostly whisper: methane, a gas that on Earth is practically a billboard for life, given that 90% of it comes from biological sources. But on the barren, rust-colored plains of Mars, its sudden appearances and disappearances have sparked one of the most heated debates in planetary science. Is it seeping from hidden microbial colonies deep underground, or is the red planet simply belching geological secrets we don't yet understand? NASA's Curiosity rover has been the star witness in this cosmic courtroom drama. Since landing in Gale Crater in 2012, its instruments have recorded erratic methane spikes, short-lived bursts where concentrations soar to 10 times background levels, then vanish within days. The most dramatic spike hit in June 2019, with methane levels rocketing to 21 parts per billion. That's not much by Earth standards, but for Mars, where UV radiation and chemical reactions should destroy methane within centuries, it's a glaring anomaly. These spikes aren't random noise, they're localized, repeatable, and maddeningly unpredictable. The plot thickens with data from Europe's Trace Gas Orbiter, a satellite designed specifically to sniff Martian methane from orbit. While Curiosity catches whiffs of gas at ground level, TGO's ultra-sensitive spectrometers have found nothing, not a trace. It's as if Mars is playing a prank, offering one set of clues to the rover and a completely contradictory story to the orbiter. Scientists have scrambled to reconcile the mismatch. Maybe methane lingers near the surface at dawn when Curiosity takes measurements, but dissipates by the time TGO passes overhead. Or perhaps Gale Crater is a methane hotspot, its unique geology releasing gas that doesn't reach the broader atmosphere. The biological angle tantalizes. On Earth, methane belches from wetlands, livestock, and even termites, all life-driven processes. Some microbes, called methanogens, thrive in oxygen-free environments like deep underground aquifers, exactly the sort of niche that might exist beneath Mars's permafrost. If Martian microbes are producing methane, their emissions could be sporadic, tied to seasonal changes or even daily cycles we don't yet grasp. But geology offers compelling counterarguments. Mars has active volcanoes, or at least it did in the geologically recent past. While none are erupting today, residual heat could be serpentinizing rocks, a process where water reacts with olivine to produce hydrogen and, yes, methane. Or the gas might be ancient, trapped in ice cages called clathrates for eons before occasional cracks release it in pulses. The stakes couldn't be higher. If the methane is biological, it would be the strongest hint of extraterrestrial life in history. If geological, it rewrites our understanding of Mars as a dead world. Future missions like NASA Mars Life Explorer aim to settle the debate by hunting for isotopic fingerprints, carbon signatures that could distinguish between biotic and abiotic origins. Until then, the methane mystery lingers, a puff of gas that could mean everything or nothing at all, but refuses to be ignored, perhaps the most intriguing possibility. Both stories could be true. Maybe Mars is a world where geology and biology conspire to keep us guessing, each methane spike a riddle wrapped in a red dust enigma. One thing's certain, this isn't just about gas. It's about whether we're alone in the universe and whether Mars has been quietly holding the answer all along. In 2011, astronomers spotted a cosmic train wreck in the making. A massive gas cloud 3 times Earth size, hurtling straight toward Sagittarius A, the supermassive black hole at our galaxy's heart. Dubbed the G2 cloud, this doomed wanderer should have been shredded into cosmic confetti, its gases spiraling into the black hole's maw in a brilliant display of astrophysical violence. But when the moment of truth arrived in 2014, G2 didn't just survive its close encounter, it emerged almost unscathed, leaving scientists scratching their heads at an object that refused to follow the rules. The anticipation had been electric. Black holes don't play nice with intruders. As G2 approached its closest point, just 260 times Earth's distance from the Sun, models predicted tidal forces would stretch the cloud like taffy, heating it to millions of degrees until it glowed in X-rays. Some simulations even suggested the ensuing light show would outshine the galactic center for years, but the real show was underwhelming. Rather than a spectacular fireworks display, G2 slipped past with little more than a flicker, its structure remaining suspiciously intact. It wasn't acting like a free-floating gas cloud at all. It was behaving like something far denser, something with hidden structure anchoring it against the black hole's pull. Theories exploded like supernova. Could G2 be cloaking a stealthy stellar core? Stars, even small ones, pack enough gravity to hold their own against tidal disruption. If G2 was really the outer envelope of a low-mass star, its resilience made sudden sense. Supporting this, infrared observations revealed the cloud's motion wasn't erratic but smooth, consistent with an orbiting star dragging a cocoon of gas behind it. Maybe an old binary star merger had birthed this hybrid object, a star wrapped in a gaseous shroud masquerading as a simple cloud, but the plot thickened. If G2 harbored a star, why didn't telescopes spot the telltale heat signature? Some researchers proposed an even wilder idea. Maybe we're seeing a new form of black hole feeding. Traditional models assume accretion, the process of matter spiraling into a black hole, happens in a chaotic, continuous flow. But what if Sagittarius prefers bite-sized snacks? G2 could be part of a larger population of dense gas clumps, nibbled apart over millennia rather than swallowed whole. This modular accretion theory would rewrite our understanding of how black holes grow, suggesting they might gain mass in fits and starts rather than steady streams. The aftermath only deepened the mystery. Instead of fading away, G2's stretched out debris later flared unexpectedly in infrared, another curveball. Was this delayed heating from hidden shocks in the gas? Or evidence of magnetic fields threading through the cloud, resisting total disintegration? Even stranger, G2 wasn't alone. Its sibling, G1, had made a similar journey years earlier with equally puzzling resilience. Were these objects part of a cosmic pattern we're only beginning to recognize? What makes G2's survival so electrifying isn't just the defiance of expectations, it's the doors it's kicked open. Whether it's a hidden star, a new accretion mode, or something entirely unforeseen, this cosmic survivor proves black holes don't always play by the textbook. Every anomaly in its behavior is a breadcrumb leading toward a deeper truth. that the universe's most extreme environments still hold secrets we've barely begun to decode. And as telescopes train their sights on Sagittarius A, waiting for its next meal, one thing's certain: the galaxy's heart still has surprises up its sleeve. The universe is expanding. This much we've known since Edwin Hubble's groundbreaking observations nearly a century ago. But here's where things get strange. Depending on how we measure this expansion, we get two wildly different answers, and this discrepancy isn't just a rounding error. It's a full-blown crisis in cosmology known as the Hubble tension. On one side, we have the cosmic microwave background, the afterglow of the Big Bang, which suggests an expansion rate of about 67 kilometers per second per megaparsec. On the other, measurements of nearby Cepheid variable stars and Type Ia supernova peg the rate at 73. That 6-kilometer gap might sound trivial, but for a universe governed by precise physical laws, it's like discovering your GPS and odometer disagree on how fast you're driving by thousands of miles. Cepheid stars, our cosmic yardsticks, pulse with a rhythm directly tied to their true brightness. By comparing this intrinsic glow to how dim they appear from Earth, astronomers can calculate distances with stunning precision. Supernova, the violent deaths of white dwarfs, serve as even more distant markers, their uniform explosions acting like standard bulbs in the cosmic dark. When we chain these measurements together, they paint a picture of a universe expanding faster than our best models predict. But the cosmic microwave background, captured in exquisite detail by missions like Planck, tells a different story. This ancient light, frozen in time just 380,000 years after the Big Bang, reflects a slower, more sedate expansion rate when extrapolated to today. The implications are staggering. If both measurements are correct and repeated observations suggest they are, then something fundamental is missing from our understanding of cosmic evolution. Maybe dark energy, the mysterious force accelerating expansion, isn't constant but grows stronger over time. Or perhaps the universe isn't as homogeneous as we thought, with giant voids or invisible structures skewing local measurements. Some theorists even float the idea of early dark energy, a transient phase in the universe's infancy that left subtle fingerprints on the CMB while nudging present-day expansion out of sync. Then there's the nuclear option. What if the standard model itself is incomplete? Tiny tweaks to the number of neutrino species or the exact nature of gravity could bridge the gap, but each adjustment risks unraveling other carefully tested predictions. The Hubble tension isn't just a puzzle, it's a potential crack in the foundation of modern cosmology, a whisper that the universe might be playing by rules we haven't yet written. Until we solve it, every measurement, every model carries an asterisk, a silent admission that the cosmos still holds cards close to its chest. And that's the thrill of the hunt, the chance that today's biggest headache could become tomorrow's breakthrough, rewriting the story of everything we thought we knew. From vanishing stars to rogue radio bursts, from phantom galaxies to whispers of methane on Mars, each of these 30 cosmic mysteries is a humbling reminder of how vast our ignorance truly is. But here's the beautiful paradox: every unanswered question, every confounding anomaly isn't a failure of science, it's a beacon. These enigmas are the universe's way of nudging us forward, daring us to look deeper, think harder, and rewrite the textbooks we once thought were set in stone. Consider this: a century ago, dark matter would have been dismissed as fantasy. Black holes were mathematical curiosities, not reality. The idea of planets beyond our solar system was pure speculation. Today, those frontiers are just the starting point. The mysteries we've explored, whether it's the WOW signal's eerie silence or the Great Attractor's gravitational pull, aren't dead ends. They're invitations. Every time a telescope captures something that shouldn't exist, every time a rover beams back data that defies explanation, we're handed a gift: the chance to peel back another layer of the cosmos and discover something revolutionary. And that's where you come in. Space isn't just for astronomers in lab coats, it's for anyone who's ever looked up and wondered. Maybe your late-night stargazing sparks a question that leads to a breakthrough. Maybe sharing that bizarre space fact at dinner tables a future scientist. Curiosity is contagious, and every great discovery began with someone refusing to accept "we don't know" as the final answer. So keep questioning. Dive into the comments and tell us which mystery haunts you the most. Is it the hexagonal storm on Saturn, or the way Oumuamua defied all expectations? Hit subscribe to join us as we chase down answers, because the next cosmic revelation could drop any day. And remember, the universe isn't just stranger than we imagine, it's stranger than we can imagine. The only limit, our willingness to keep exploring, because here's the ultimate truth: science doesn't fear the unknown, it thrives on it. And somewhere out there, hidden in the darkness between the stars, is the next great mystery waiting to be found.